The interesting part of circuit design starts when we add sequential elements into the combinational logic. So, combinational logic alone cannot achieve much, and no circuit is pure combinational. So, we'll have sequential elements, a lot of sequential elements, and two major sequential elements are used in the industry. One is D Latch and DFlipflop. So, other flip-flops and other latches that you've studied in textbooks are not actually used in the industry. So, because of the simplicity and the reason that they meet the necessary objectives, these two sequential elements are the most used. In fact, D flip-flop is the most used and D latch is like a half D flip-flop. In a processor scenario, D flip-flops are used in pipelining. So pipelining is the concept of dividing your bigger block into smaller sections so that you can increase throughput. And maybe latency might decrease a little bit, but throughput is what you are interested in. Throughput is the number of outputs per second, you can call it, or it could also be measured in instructions processed per second. Pipelining is the process of dividing your bigger module into smaller sections. Say, for example, your processor pipelining stages could be opcode fetch, decode, execute, and write back. So these four sections will have flip-flops in between them. You must have studied in topics like computer architecture, which is very important for anybody who gets into processor design. So your first instruction is fetched, and in the next clock, this instruction is given to the decode stage. While the decode stage is working on the current instruction, a next instruction will be fetched, and the decode stage will pass on to the execute stage, and the opcode fetch will pass on to the decode, and a new opcode fetch will come in. And in the next clock cycle, execute stage will pass on to write back, and decode will pass on to execute, and opcode fetch into decode, and a new opcode fetch will arrive. So all the four stages will be simultaneously processing, and even though the first time it takes a while for the output to come out, after the first time the delay is only this much. So each of the smaller sections take less time to process. So the delay is only this much, which is your clock period, right? So D flip-flops are extremely helpful in implementing pipelining. The other reason D flip-flops are used is for synchronization. Say, for example, your input is coming into your chip, and we'll never know if your input is stable or varying. So if you want to take a stable input into your chip, you will put a series of D flip-flops and synchronize your data. So the data that is coming out of, say, second or third flip-flop even will be a stable value. Or for example, you have two combination logic and they are feeding data into another combination logic. So to ensure that both the data is getting into the third combination logic at the same time, we will put flip-flops, and ensure that the data that is going into C3 from C1 and C2 is going in at the same time. The other reason could be to avoid glitches or hazards. So there could be some unwanted variations in your combination logic. Say for example, you have two different paths, right? So say path A and path B. So path B might reach the output faster, and the path B, since it reaches faster, it might give a temporary change in value at the output. No, so this is called a glitch. And similarly, hazards. No, so if this unwanted change at the output, it could trigger the next logic. Say for example, another C1. No, so this positive value could trigger another C1, and it could have a chain reaction. To stop that, we will put a flip-flop, and we will only register the value after all the paths have settled down. After all the paths have settled down, then we will register this value and pass it on to C1. And D flip-flops also help us fix the clock frequency of the circuit. So clock is the signal that governs timing of your circuit, and when data is valid on the data path, when data is invalid, and so on. No? So because of flip-flops, your timing is very clear. No? So clock period is calculated based on flip-flop through combination logic to the next flip-flop delay. So how much is this delay? And that is what is your clock period, T clock. So 1 by that will be your frequency. So you have a minimum T clock, and your clock time period should be above this. So it'll be little above T clock to give some buffer, and you can fix the clock frequency based on that. You want to isolate a block in your design. So then you think of D flip-flop. Say for example, you have a module 1. So if you want to isolate this, say this module in some mode inside your chip, so you put something called a wrapper. So this wrapper is just a combination of flip-flops and muxes. So either before the flip-flop you put a mux, or you put them after. So if you put them after, another path will come from, say, another flip-flop. You can also think of it as bypass logic. So you kind of bypass this module 1 and go out without getting into the module. The other places we'll need flip-flops are in sleep modes. Say if you want to dynamically cut off a block or cut the clock to the block, so you'll put a mux. So this is one way to do it, and feed the mux from a flip-flop, right? So if this value is 1, then you're gonna say just give a stable input, or else you give clock, right? So based on your flip-flop, you can decide whether to feed clock into this module or block or not. So these are some of the common purposes of flip-flops. In many places you can also use latches, but latches you'll have to be careful. Next we will discuss about flip-flops and latches.